Hey, Mr. Ruth here. This is part two of video number two of lesson 10. All right, so part two is area-based optimization problems. I think optimization problems are some of the neatest problems that we solve in all of mathematics. In fact, a lot of calculus is used in solving optimization problems. So you're kind of getting a sneak preview of some of the more basic problems that you'll ultimately be solving in calculus your junior or senior year. But before we can start solving these problems, we need to figure out what this word means. What does it mean to optimize something? Well, to optimize something means we're trying to find the best possible value. Now, most of the time that means we're either trying to maximize it, and then let's say we've got a problem and we're talking about money and we want to have the most money possible, or the most number of McDonald's tokens, or the most number of Baja Blasts, or something that's good. Or we could be trying to minimize something. We're minimizing tardy violations, or we're trying to minimize a golf score, or minimize our costs if we're talking about money in that sense. So that's what optimization means. We have some sort of problem and we're trying to find the best possible value. And that's either going to be a maximum or a minimum. And you kind of have to read the question and kind of look at the context in order to figure out which that is. Let's look at an example. You have 20 meters of fencing and want to fence the largest rectangular area possible. What should the length and width of the fenced area be? So I've got 20 meters of total fencing. And I'm making some kind of rectangle. So just kind of thinking through this. Whatever the length is on one side, it's going to be on the other side because it's a rectangle. So I've got some kind of situation like this, and then I just can say, well, let's just throw a number in there. Well, if the width was 8, then the width on the other side would be 8, and then these two values, the other two sides of the rectangle, if all of it's 20, then I know 20 minus the 8 gives me 4 left. And since these two sides are going to be equal, I know that these two are each going to be 2. And I can quickly kind of think through, oh, I see how this is going to work. The length plus the width is always going to add up to 10, right? Because if this was going to be 7, and this would be 7, and that would mean that this has to be 3 and 3 for all the red numbers to add up to 20. So I can kind of look through the different pairs and figure out, oh, well, what area do I get from this pair? What area do I get from this pair? And I could just do a lot of guess and check. And that's one way to solve these problems. If I go over to Desmos, I can say, all right, when I had 7, that gave me 3, so that's 21. So I could say to myself, when the width is 7, the area is 21, and I can actually plot that as a point on Desmos. And then I could say, all right, well, what about when the area is, the width is 8? When the width is 8, the length has to be 2, and that gives me an area of 16, so I could plot that point. When the width is 9, the length has to be 1, so the area is 9, so that gives me that point. When the width is 10, that's kind of weird. If the width is 10, the length is going to be 0, and I'm not even going to have a rectangle at all. That's a point. Go in the other direction. When the width is 6, the length is 4, so that gives me 6, 24. When the width is 5, the length is 5. That gives me an area of 25. Now, some of you, on the other side, when the width is 4, and the length is 6, so 4 by 6 is the same as 6 by 4. So I realize that all of these are just symmetrical. This is just an example. I'm not asking you to do this in any of our questions, but I want you to notice when we graph all of these individually, what shape does this form? This forms a parabola. That's because the answer to this question involves quadratics, okay? And that's what we're going to be using. Now, when we want to maximize the area, what part of this parabola am I looking at? Well, I want to maximize, so I want to look at the tallest possible point of the parabola. I care about the vertex. Okay, so when we're trying to optimize, when we're doing maximization or minimization problems, what we're really saying is, where is the vertex of the parabola? All right, let's flip back to the notes. There's a methodology that you can use for most of these problems. All right, sketch a large clear diagram. We've already done that here. Construct an equation. So we're going to use this method for this problem. Construct an equation with the variable being optimized as the subject. All right, so the subject means it's going to be on its own on one side of the equation. So I'm trying to maximize area, so I need an equation that's area equals something. Well, here it's pretty simple. It's just length times width. Easy enough. Step 3, use the constraints of the problem to construct another equation. All right, so what else do I know? Well, I know that the perimeter of this rectangle is 20. Well, what does that tell me? That tells me that P equals 20, but the perimeter of a rectangle is 2 times the length plus 2 times the width, and that equals 20. So now what I have here is I've got two equations, each of which has L and W in it. So here's the key step. What I want to do is solve for one of these and then substitute it back into the area equation. So I need to solve, let's say I'm going to solve this one for L. Okay, so what do? Well, if I divide every term by 2, I get L plus W equals 20. And then I can subtract W from each side, and I get L equals, oops, not 20, 10. L equals 10 minus W. So now I'm going to take this and I'm going to substitute it in for L here. So I rewrite my original equation, area equals 10 minus W times W. Now, at this point, depending on what the question's asking, I might do a number of different things. Most of the time, to solve the equation, what I'm really saying, solve is maybe not the best word, what I'm really trying to do is say, type in the equation and find the vertex. And I'm looking for the vertex. So here, I'm going to change area into the y. I'm going to change the w's into x's, because Desmos can't handle w's. And I'm going to graph this. Y equals 10 minus x times the quantity x. And for this particular example, I'm just going to graph it on top of here. What do you know? The parabola that forms is exactly the same parabola that I got from all these individual points. Now, just to be clear, when you're doing these problems most of the time, I am not expecting you to plot all these individual points. All you're going to be doing is graphing this parabola. Where's the vertex? 5, 25. Now be careful to recognize what the x and y coordinates correspond to. The x coordinate was what? What was the variable here? Well, that was the width of the rectangle. The y coordinate was substituted in for the area. So what this tells me is that when the width of the rectangle is 5, the area is 25. Eliminate any duplicative or nonsensical solutions. Sometimes this is relevant, oftentimes it isn't. And finally, be sure to answer the question asked. This asks me for the length and width of the fenced area, so I would say it is 5 by 5. What were my units? Meters, so I would make sure to include that. Okay, on to the next video.